Our next and last speaker before lunch break is Stephan Sahm. Let's welcome the speaker with a warm applause. And he will talk about IsDef.jl maintainable type-inference.
Okay, there we go. We're a bit earlier, but I think that's great. I prepared a talk for you today. We have actually 30 minutes. So this, the 10 minutes lightning sessions, they've been just previously, and now we have actually full 30-minute sessions. So yeah, a bit more relaxed. And we have time. I'm glad for every question which pops up. So I'm Stephan Sahm. I founded JuliaCon.io. You see it also on the sponsorships. So that's me. And yeah, it's my baby. I'm really fond of spreading Julia within Central Europe, so Germany based. And this is actually not related so much to Jolin. It's really just one of the packages I wanted to have for a long time. And yeah, it took quite a while. You see. So we talk a bit about types today, and we talk a bit about traits. And this traits part is actually the one which motivated me. You're going to see. Okay, so let's start. So 3 parts for today. First, some teaser on type inference. So why is this actually an issue? Yeah, maintainable type inference. And yeah, second part, I want to give you kind of what IsDef can offer you, just a quick summary, and then going to this motivating example of interfaces and traits. And last, because we have a bit of time, I also want to give you details about how this actually works. So and I think this is going to be a lot interesting because we are using some code rewrite. So this was actually my first package using the meta infrastructure of Julia in a bit more depth. Okay, so let's start. Julia's type inference. Yeah, you can kind of see it. So this is the motivating example, and I think can zoom a bit on. Yeah. So type inference in Julia is really not meant to be used by you. This is an implementation detail, which is there to speed up your code. And there are some edge cases, and I was looking kind of for a really good tiny edge case, which gives you the idea that this is magic, yeah. And this one is nice, yeah. So it's really super tiny, very recently reported. So if you have a vector and a vector, then the standard base type inference method promote up is actually not knowing anything about this. Yeah, it's just returning the default type inference value, which is any. So might be a failure, might be something, might be anything. And yeah, and this just happens because it's not meant to be kind of used as an end user. It's really just meant to be used to improve your code. And yeah, so that's the issue, and these things, they may change actually from every minor Julia version to another, because yeah, that's really an implementation detail. This is actually not so much of a problem, yeah. So usually no one uses this, or only a few persons, and actually no one should use it in a sense. But it's really not a problem because it's used to decide between compile time dispatch, if you want, or runtime dispatch. So from a semantic perspective, you're never facing it if you're really just using it for the standard use case of performance optimization. So yeah, the only case would be you want to optimize some performance. So yeah, you profile your code, you see, okay, here's some type inference is missing, and then you fix it. Yeah, you go somewhere around. So in this case, you would maybe use static arrays or something to improve the type inference. The official documentation actually makes this also very clear. There's not much documentation to be found on this, but the promote up actually has documentation. So this is really just a copy and paste of the standard Julia doc. And you see this little warning: due to its fragility, use of promote up should be avoided. It is preferable to paste the container element type on the type of the actual elements. Only in the absence of any elements, it may be unavoidable to call promote up. And even for for the absence of any elements, it's still recommended actually to not use this because it's unstable and just might change from any version. Yeah, so I was hearing such responses when I tried to use the type inference system for my own cases, for trades namely. And yeah, and it took really a couple of years until I came up with a bit more stable approach. So now I want to kind of show you the IsDef package. So this is the very summary of it. Yeah? So you get kind of two little functions. The one IsDef, which gives the package the name. It just checks whether a given signature is defined. Not in the sense that you find kind of the method somewhere, yeah, which might just point to another method which does not exist for your types, but it's really type inference that works. So it checks whether this actually, yeah, has a proper type inference to some type, and yeah, not failing. And because this is type inference, there's also another function which I call out, capital, bless you. And yeah, and this is kind of the thing which is used behind the scene, which is really then just a wrapper around Julia's type inference. We're going to see a bit more details on it. For convenience, because in the trades application, you always rather use values, yeah, or it's at least handy in Julia to just pass values around and don't care so much about all the type annotations. I have kind of these two versions, the one falling back to call the type of all arguments, and the difference is explicit. So if everything is a type, we just take them as types. If there's some value, we take everything as a type of everything. So it's always kind of a trade-off how you can, yeah, how to make things convenient and easy to understand and stable, and this is the trade-off. Okay, so let's take a look. So we have now our little example here, yeah, and if you use IsDef, you practically have kind of one layer in between. So you can actually now fix this for yourself. Actually, I admit this should be a part of IsDef itself. So if we want to fix space, yeah, it's good actually to not fix it in your own package, because then someone else might have another fix for it. So it's good to have a central place to fix it. And this would be naturally IsDef itself. But as of now, it's currently not yet in the extra rules. I'm planning to add it. But still, it's a good example to visualize kind of how we would fix this. So if we use our out function here, just zooming in a bit, yeah. So we can just define this out syntax here. That's a special, this is kind of the method call under the hood, which everything else translates to you. You have this convenience functions on top. And here you see we expect a tuple type. Yeah, and the way in Julia we can dispatch on this is just specifying type, curly brackets, and then you have the full tuple type. This gives a little boilerplate, but it's really kind of from everything which I tried out with the less boilerplate. Yeah. So you then just type your function signature, all in types. And we can use kind of where syntax. We check kind of all these things. We have a vector and a vector and specify that our little t is a number. We can do all the stuff. It's just normal Julia dispatch, yeah, just now on the type level. And this is the mean which the package gives you mainly. Yeah, so this is the key reason why this is now getting maintainable. So if something changes, yeah, you can fix it. So maybe you have your rule right out of the box. So yeah, you can put it there, but just in case you see kind of from a minor version change to another, there's something breaking. This is now the way to control it. And yeah, and this works. So a little zoom in is not good enough for here, but even such an abstract dispatch rule is, yeah, totally fine. So yeah, just does it. And yeah, and this infers also. So I haven't put the type inference over here, but so now if you apply Julia's type inference mechanism to this is really statically doing it. Of course, depends on your code, yeah. But yeah, so this what is statically inferable is statically inferred. Okay, so what's the time? Perfect. Okay, so now I want to introduce you kind of to my motivating application. So I mean, it's also already motivating to see kind of this breaking, yeah? And oh, if something breaks, you want to fix it, even if you don't know where to use it for. But this is now a real application. So I've been working with trades when I transitioned kind of from Python to Julia, because multiple inheritance is just not there in Julia. And if you would like to map it, then traits are kind of the most natural step to go for. So there's one motivating example for traits, and here I have kind of just a simple example using the standard interface in Julia, the iterator. Yeah, this is kind of Julia's default traits-like thing. And yeah, here's some example with iterator size and iterator element type. We just want to do it now on a single element vector or iterator. I call it single. And this would be, bless you, one example how you can use traits in Julia. So if you haven't seen this before, bear with me, it's kind of not so complicated as it looks. We really just have kind of multiple inheritance in the sense that we have a first function call, yeah, and then we get some extra type information from the given value. So we have this iterator element type or iterator size. They are real base functions, yeah, you can use them, and give them as extra input to a second function, dispatch, where we now dispatch on these extra information. So this is standard, Julia traits, do-it-yourself style, yeah. And this works well, yeah, this is kind of nice. And you can kind of then call the function and it works and you're sure, okay, my things are defined. And the way this works is, as you see, you have these helper functions, yeah. So this is the way current Julia uses traits. There's documentation on it. And yeah, so every of these traits, extra definitions, they usually represent one or two functions. Yeah, so you really define that you defined some functions. And of course, yeah, getting into Julia, I thought, man, yeah, this is real boilerplate. Yeah, so it would be nice if I don't have to write this, but it just now because I already defined the function. So this is the motivation, and as you can see, yeah, this is now solving it. Took a while, but yeah. So using the IsDef traits, this is a bit how it looks like. And yeah, so we have, again, let me zoom in. We have again our little definition, yeah. And instead of having our extra, perfect, thank you so much. I got a little time update over here as well. We are not having extra definitions of these traits types which correspond directly to methods, but we now can just check them directly using our maintainable type inference. Yeah, and this looks still a bit ugly, so wait for the second part of this slide set. Yeah, so we have in Julia this val type, which gives us the possibility to dispatch on, let's say, bit values. Yeah, and it's a bit more complex, I think, than that. But yeah, just everything which you can imagine as bytes, you can dispatch on this. And we can now give us very similar two-function dispatch and get the same result. And now this is kind of safe and yeah, and maintainable, which it wasn't before. So yeah, it took me a couple of approaches. Yeah, and this is the reason why I wanted to have, why I wanted to have maintainable type inference. We can make this look much nicer. And because of this motivation, I actually already launched a package, some of you may know it, where traits, which gives you this unbelievable lovely syntax to do this nested function dispatch. Really, really concise, and for me this is kind of the preferred way to do the traits. So yeah, it does not enforce kind of some specific interface. Yeah, if you think of traits, this is always another motivator. Yeah, some don't focus kind of on this multiple inheritance in a Python super flexible dynamic style, but they rather focus on having a predefined set of functions which need to be defined, some IDE support or something. So just to clarify it up front, this is not doing it. Yeah? This is really just a nice syntax for this nested dispatch. No enforcement of kind of this function needs to be defined for your type or this function. It's really just making this nested function call simpler. Yeah, I'll zoom it then. Thank you so much. Yeah, well, that was a bit off. Okay, there we are. So this is the traits macro from where traits. And you see it's really envisioned, yeah, to work with something like IsDef. And yeah, it's out there for a couple of years already. So you do it now really in one function definition, and you have an extended where syntax where you can put all these extra parts. And it has support for these standard Boolean return functions, yeah, these property functions. So because they are so common. And yeah, there is also support for other things, check out where traits, but in this case, this would be the syntax it now goes back to. A nice string of where traits is now that you can actually also overload this from other packages. Imagine kind of this nested function dispatch, yeah, it's just a side note. You can always overload the first one, yeah, but it's really tough to now get into the second from another package. And this is kind of one difficulty with traits, and this is taken care of if you use the where traits as well. So you can actually add further traits from other packages as well. Okay, so this is the motivating example, and yeah, the final syntax I'm using then to build my trait stuff. And yeah, and this is now safe to use. Okay, for the final time, I would like to go into some more implementation details. But first, I think it's a good time to pause. I think, yeah, this is really going to the implementation details. Are there some more questions for this part so far? Please, over there.
How do where traits interact with this guy?
So I think for the question was how where traits interact with multiple dispatch. So it's really just the very same as you saw doing it yourself. Yeah, this is a macro. It just rewrites the code to this nested function. And the way it kind of handles that you can overload it from somewhere else is that you, of course, need to use the traits macro itself. And it will just regenerate all the code. Yeah. So if you use the traits, it's kind of idempotent in the sense that it always generates the fully valid traits implementation and makes sure that all the line number annotations kind of point to the right things, and also makes sure that documentation kind of matches. But this is kind of the main trick. It just regenerates everything anew if you define kind of a new traits sub-implementation. Thank you for the question. Excellent. Please, another question over there.
Is it simple to use IsDef to test whether a type conforms to an interface, like to verify that, like in a unit test?
Yeah, thank you for the question. The question is whether we can kind of use this type inference, especially IsDef, to now check for an interface. Yeah, and I think, yes, sure. So you can use it to check whether it complies. The same like you would use it in this traits dispatch. Yeah, there's kind of similarly. And I think this is also the Julia way to think of it. Like you really want to have this testing. I think it's even better kind of if you have a real applied test, yeah, to check that the whole pipeline really works and not only the type level works with it. And by this you would kind of implicitly also get the type level. But I also like actually to put some check whether method error is thrown for something, yeah, in my testings. So I also like this type level stuff. So yeah. Great question, thank you. Okay, then going on to some implementation details. So happy details. I have 4 things to go on. I hope time's. Yeah, I think we should have enough time. So main and most important part of this is actually code generation. Because, yeah, you need to do some type inference, and there will be a time where you fall back to something clever than you, which is Julia's default type inference. But because it's so unstable, I was really looking for kind of a way to get the first steps right. Yeah. So kind of the simplest wrappers, yeah, that they don't need to fall back to Julia's type inference. This is where code generation comes in. So I take the part of your code and rewrite it. Inspection, we're going to look into inspection, how you can actually kind of get a bit more feeling what's actually going on under the hood. Like if you want to debug some of these things that you really can easily look into it, what's going on. Val types is another special thing because you, as mentioned, you have like this bytes types, which you can actually put into type level things, but they can also move around as normal values. So there's a bit of a combination. There's a special handling for this, and then also some notes on error handling. So let's go to code generation. I wanted to kind of summarize the rule which is implemented in the package. So it's, yeah, it sounds a bit more complex, but I think it's easy to get. So if the types are not all from Julia base core, so imagine we do this function call. Yeah, we have our signature, we check whether our element type function is defined for this or that. Yeah, and if all these things which come into IsDef, yeah, are from Julia base core, and we have code generation supported for this, then we use code generation actually. So yeah. So what's supported? We have args, keyword args, if else, plain statements and macros. We have not supported loops. So that's kind of key thing. Loops are actually quite hard to get code rewrite for it, and I just fall back to normal Julia inference. But still, it does for a lot of things. And here's one example to it. So having kind of this most complex thing which is supported. If you have just an if else method, yeah. That's a very simple implementation, but it has some branching under the hood if you compile this to intermediate representation. And now this actually supports this third case, which appears in types, which is kind of that you don't know. Yeah. So check this. We now use the val types I already mentioned. You have a special way to inject kind of these values into the type system, which is this val type of function. And yeah, and now we can kind of get really all three cases. And they are used also in the standard fallbacks, so you don't need to get this in detail on yourself, but it's good to see. And this kind of thing works just by code rewrite. This is not going back to Julia inference, but uses code rewrite to really do it statically. Okay, so inspection. So if you want to get more details, kind of what is going on under the hood, this is really nicely refactored so you can inspect it. Take a look at the code. It's really, I think, easy to read and understand. And yeah, and we have kind of some further support. Actually, okay, dealing with the Zoom. So if we have a little tiny example, yeah, like such a wrapper, yeah, this is actually also a good motivating example why you need this. Yeah, you have a wrapper which does something on top of your normal function call, and if you now use has method, yeah, which would be kind of the naive approach to something like IsDef, then you're already failing because this function is defined for everything. Yeah, so it doesn't give you any information about whether this function is really defined for your type in a useful manner. So we have a wrapper which wraps something totally arbitrary. I just made up with some types here. And we see our outer wrapper is working. Yeah, so it also everything infers. We have also support for the bits types. And we can now call code lowered, or using the IR tools package. It looks a bit more concise to me actually. The code IR. And you see, if you use the tuple signature type, yeah, so this is the real machinery under the hood, yeah. If you use this one, and you can inspect kind of what code is generated, and it's really built in such a way that you can now read it. So this is going into the wrapper, yeah, and yeah, so you see that this apply iterate, which is kind of using the dots, yeah, the splash one. This is now really wrapped. Okay, 4 minutes left, so whew, let's get there. Okay, so we have also an out debug, which is now doing the things iteratively. As you've seen before, okay, we only had this first layer, yeah. So if you really want to understand what's going on, man, so how do I get in the next layer? And out debug is just for this. So here we can really see all the different layers. So some extra information, then it goes deep into it until it really returns, and you have all the details. This again using IR tools magic to rewrite your code and add this extra debugging outputs. So that's really handy, and yeah, was handy for developing, but I guess also helpful for understanding what's going on, so that this is really transparent, which is a great important part of maintainability. Okay, only a few times left. So val types, just to mention it. There's a special val type of, which which is kind of a function which just grabs these types extra, and it's used internally as well to kind of improve the inference part. Because if you use just literal values in your code, yeah, we can use them for type inference. They are not dynamically, they are static. We can use them, and yeah, and you also need to define them yourself. If you make this definitions yourself, yeah, check that if you have kind of some val type like bool, you also need to account for the case that it's a val type. That's kind of the downside of it, two different cases, if you have a literal value or not. We have also some helper values for some helper methods for this, like a signature without val types function to help you along getting rid of this extra performance improvement. Okay, some information about errors. I think I'm going to skip this to get more time for discussion. Yeah, so we have there's extra error handling in it. Yeah, going back if you have more time. So let me summarize. So what you see today is IsDef, which is therefore maintainable type inference. You've seen kind of one motivating example. The minus of a vector and a vector with a number is really not working out in current Julia. And we can easily fix this if we have some maintainable layer on top of it of standard type inference. So usually you are actually not motivated to use this at all. Yeah. So if you have used it, you're probably some niche Julia user, but now you can actually use this safely. And one motivating example to use this kind of in the mass is really this traits case. Yeah. So there, you yourself may want to use type inference to get rid of the boilerplate. Okay, we've seen some implementation details. So you have code generation, which does good for kind of a couple of standard cases, but it falls back to standard Julia inference. It will warn you in case it's just unsure. This is not a good idea to go back to standard Julia, but it still does. We have some support for byte types to get better inference, and we have kind of also some further error handling so that you have a good feedback when it's going to get unsafe. Okay, that was a lot. I want to have a few seconds, like to mention. Check out cloud.jolin.io, recent thing of this company, deployment of Pluto. You may love it, and I'm really looking for testers. So yeah, check it out. And meant for companies in the end, so to use Pluto, and may also be something for you. Reactive notebooks, I want to spread them in Germany and Central Europe, and yeah, if not also to you, that would be great. Okay, so then thank you very much for being with me for this talk. I have a couple of open questions we can also discuss further. You can reach me anywhere, so get my contact details, scan this nice QR code, and yeah, I'm happy to get more questions. Thank you so much.
Thank you for the talk. Are there any questions? Yeah.
Yeah, please.
Talk about the difficulty of handling loops. Can you handle recursive function calls? Do you handle a nested function?
Nested function calls. That's a good one. I think this didn't pop up because this package is working on intermediate representation, and you find loops in intermediate representation in the sense of jumps, which are kind of recursive. But I guess nested function calls just don't pop up on this level. So yeah, never encountered. Yeah.
A tail recursive function, would that make it easier, or? I don't know a ton about that.
Yeah, not sure. No, it's really tough to get into this really detailed. So we would have to look into more details offline, I think. So because this intermediate representation is a different way of thinking about Julia, and yeah. But thanks, cool question. Yeah.
We have other questions?
Question, I think you have question over here.
Thanks a lot for the talk. So actually, this is something that we need in Jump. In mutable arithmetic, we always need to do this. And currently what we are doing is that we need to hard-code the promote operation method for every type we have. And if it's not hard-coded, we default by coding the operation on 0 of the types. Which doesn't work, for example, if it's a division.
Yeah.
Sometimes it's one and so this is quite interesting. And something I don't quite understand is why is if what you're doing is better than call the compiler that return type, why is this called and compiler that return type not doing it?
Yeah, so there was some application for this. That's nice. I'm looking forward. Let's sync. And the question kind of core compiler.return type, which is the main machinery. That's kind of the core function. I mentioned promote op, and core.compiler.return type is another interface to this. And it has the same difficulty as upfront. So I mean, you can kind of also overload this, yeah, but it's not intended to. Yeah, this is really kind of an implementation detail which you should never specialize for some own types.
What I mean is that basically return time in your package are solving the same problem. So what are the essential difference between your approach and their approach? Why do they support for loops and you don't? Why are you more accurate than them?
No, so I think it's different. So the normal standard Julia type inference is really to make this decision: can I compile this up front, or do I need to make a runtime dispatch? And this is kind of completely different target. Yeah, they just want to make this balance between not too much time for compiling, but still really lovely runtime performance. And this is just a different goal. And this is now really to use it on an end user, and not to decide between compile time or runtime, but real user-facing interface for type inference.
Very quick and doesn't care about sometimes not making the inference correctly, and you really want to it takes time to arrive to a conclusion.
That would be one way, yeah, to put it. But yeah, yeah. Okay, thank you so much.
I have time for one last question.
So there have been a couple of mentions over there. I think the first one, please.
Yeah, so kind of a basic question, but are you taking the Julia's internal type inference and patching on top of it cases to catch stuff and to fix regressions, or are you building like an entirely separate system?
Thank you very much for this clarifying question. It's about kind of whether this package is built on top of Julia's default type inference, or whether it's completely separate. And yeah, I'm sorry to not have made this very clear. It's really built on top. So it falls back to Julia's default type inference, because this is just so handy for usage. Yeah, building this on for yourself is not feasible, and I wouldn't want to do this. It's really kind of, it has a couple of cases, like mentioned, like the simple cases, if else is like the most complex, where it really falls back to custom code generation. So everything is static and inspectable by you. Yeah, this is like fully transparent. But in case this doesn't work out, it falls back to Julia's type inference. Yeah, and of course you can also always define your own dispatches. Yeah, that's also kind of this layer that's code generation and the possibility for you to specialize it or fix it in the sense, yeah, for your cases. Yeah, thank you. Awesome question.
Yep, thank you. So it's time to move to the lunch break. So let's thank the speaker once again with an applause.
Thank you very much.